Good evening, everyone. So welcome to the ATSE Victoria Division seminar. It's really great to see everybody in such a cold weather. So my name is Baohua Jia from RMIT. I'm going to MC tonight's event. So I'd like to begin to acknowledge the traditional custodian of the land on which we are gathering and pay my respect to the past, present, and emerging. So today it's our great pleasure to welcome two distinguished guests in the water sector to give us seminars. And first allow me to introduce Lara. Lara Olsen is the Managing Director of Southeast Water and Director of its subsidiary LOTA. She's also a Director of Water Science Association of Australia and Chair of the Industry and Customer Reference Group for Southern Victoria. Before joining Southeast Water, Lara was the Global Head of Business Development and Industry Products for Telstra Energy based in the United States of America. And she also led Telstra's, led Telstra's Business Development and Industry Product team for Asia Pacific. So previous roles also include Head of Strategy for City Power, PowerCore, and Australian Renewable Energy Agency, and also many other previous roles. She is the Fellow of FTSE and also Chief Executive member of Chief Executive Women. So today, Lara is going to share with us Water, the Critical Decade. So welcome, Lara.
Hi all, and thank you for having me. When I was asked to give this presentation, I was really keen to talk about water and why this decade matters so much. Partly, as Bahal mentioned, I came from the energy sector. I think often when we think about the climate and the climate change and which sector needs to change the most to respond to that, we often think about the energy sector. And we often hear about the energy transition that is underway. It's really clear to me that the same type and scale of transition is and is going to need to happen in the water sector. And so today I really want to talk about the context in terms of water and what that transition will mean, how water is involved in emissions reduction as part of the solution, and also water sector's involvement in the circular economy. So the first part of that is just providing some context around what the water sector is and our supply. So this graph shows the stream flows into the 4 major harvesting reservoirs in Melbourne. You can sort of see from early 1900s to 1997, our average there, so that first long line, is about 615 gigalitres per year. And then obviously it varies each year, but you can see the millennial drought there in the blue line. And that, although we've stepped up somewhat from that, which was 370 gigalitres a year, on average since 1997, we're about 427 gigalitres a year coming into our 4 major reservoirs. On average, it's about 50 to 70 gigalitre gap that Melbourne's customers and other water users use more than our average stream flow. Now that goes up and down, and the good news is that we do have a desalination plant, and it hasn't been on for the last 2 years because we haven't needed it, but it has been on before that. So that can help provide some of the buffer. But it's not just this picture that has changed in terms of supply, but also demand. So when we think about the millennial drought, one of the big things that has changed since then is not just the water flowing in, but our population. So we had about 3.7 million people in 2009. We now have 5.3 in terms of Greater Melbourne. So we've got 40% more population that are using this water. The other change is that a major lever we used, for those that remember the millennial drought, was around water restrictions. So in the 1990s, the average person used about just over 400 litres per person per day. That came down to about 227 in sort of 2000s and 7s, and then we'd all know target 155. In some ways, the great news is that generally we are all at about 160 litres per person per day. So in terms of our ongoing water usage, that is good news. But what it means is that we don't have that buffer that we had before in terms of asking people to reduce their water use as a way to solve this if we again face shortages. So that's the sort of supply picture that I'd like to have you to have in your mind when we talk about the different water uses. So this pie chart, and I do love data and charts, as those that work with me know, so you'll see a lot of them coming through, is the breakdown of who uses that water. So the key one that I've just been talking about there is that darker blue one, the cities and towns. But this is the critical decade, not just because we have to make sure that we can supply that water for us and our other fellow citizens, but also for some of these key other water uses. You'll see that sort of lime greenish environmental entitlements at 5%. Recent work that was done with the Victorian government and a number of the Victorian water retailers looked at how much water would be needed for optimal environmental outcomes. And that amount of water is 380 gigalitres a year if we wanted to have optimal environmental outcomes. So I want you to hold back that number, that we're already about 50 to 70 gigalitres less than we ideally need. But if we want to have optimal environmental outcomes, we need another 380 more. If we're just focused on the critical environmental outcomes, which is saving the platypus, survival of native fish, and making sure that our rivers flow in summer, we need 100 gigalitres a year. And we need it in this decade to ensure those things. In addition to our focus and desire to provide that environmental water, one of the parts of the graph that is very hard to see is that very thin sliver that goes to traditional owner water. So the water rights held in Victoria by Aboriginal people is less than 0.2%. So in addition to addressing the environmental water, we also need to look at cultural water, which is not something that we have given sufficient attention to and not something that we have worked on hard enough as a sector, but something that we know as a sector we now need to work on. Then another one of the pressures / opportunities within this graph is around industry. There's many industries, and I know that many of you will work in them, that use water. I think, and this sort of goes to show that frustration I sometimes feel when it's a focus on energy, not water. Many of you will have heard about AI and what that is doing to energy. Absolutely, there's a range of articles I read, and will AI's energy usage be larger than Japan's in 2026? Who knows? I think what I do know is that Microsoft used 37% more water year on year last year, and part of that was driven by AI. So when you hear about energy usage going up, particularly due to AI, also know that there is a large focus on water and requirement of water to provide those services. Microsoft have said that they are looking to be water positive, which is a new term I think we'll start to hear more of by 2030. And what that means for them is that they will look to put in more water from water stressed basins than they take out. And I think increasingly, as people start to understand the equations and that balance that goes with water, we'll start to see other companies both choosing to and maybe being slightly pressured to really focus on their water usage. What this means in terms of transition, and again, across the sector, we looked at different pathways for what this means. And this is something that starts to remind me of the energy transition. There's a range of adaptable pathways that we looked at, but what you can see, and there's a number of other pathways in the document for those that are interested to read it, is that that yellow section of the graph is what we call manufactured water. So that is desalination, it is recycled water or treated storm water. And in all our scenarios, pathway 5 has the least amount of manufactured water. You can see by 2070, at least 50% of our water is manufactured water. And so that's a discussion that we'll be having with our community around that. It obviously has energy implications, it has cost implications as well, and also probably in some of the different considerations that we see from industry about the use of water. often that consideration doesn't take into account that that water may not be as easily available as they think it might be, or at the cost that they think it might be. It's not all doom and gloom. The good news is that all of the technologies for this we already have, and they're increasingly getting better. And also that the water sector, the broader sector, is involved in a lot of the solutions that's associated with climate change as well. I probably should have made the font on that graph bigger than size 4, so apologies for that. I'll talk you through what those bubbles represent. Within the Victorian government, the water sector, which includes the provision of drinking water, but also the treatment of waste, trade waste and sewerage, represents about 25%. So the water sector are about 25% of the Victorian government emissions. Obviously, that's significant given they have transport, hospitals, and a range of schools, a range of other areas as well. Those two large bubbles that you can see, the blue one represents the direct emissions associated with treatment, so with sewage treatment, and then the other one is the indirect. The third largest bubble is the indirect emissions associated with water treatment. I think the exciting part about this is most of the water corporations have a net, certainly in Victoria, have a net zero target by 2030, with a number of them looking to beat it before then. And across the world now, the water sector is really focused on what it can do to lower its emissions. So increasingly, we are seeing a focus on net zero treatment plants, and they use a range of really innovative technologies, focus on nitrous oxide, both biological, chemical process, and really trying to drive that down, given often the design life of our treatment plants is 50 to 60 years. We've seen some other great technology. South Australia Water has looked at all of its pumping stations. We ourselves have hundreds of pumping stations, looking at both when they can pump that water to play on the energy market, and also have generation at each of those pump stations to make it zero cost and where possible zero emissions. I think what this does do though then is when we think about water being part of that energy transition, certainly that graph before that I showed you, one of the sections I didn't point out was that about 9% of our water entitlements currently go to power generation. So those current forms of power generation certainly use a lot of water. As some of those older forms of power generation retire, then the water entitlements will free up. That's good news in terms of increasing the availability. And often I hear people say, well, that is great news because we will just put it into hydrogen. And the only time I have ever yelled at a podcast is hydrogen podcasts. I now try and avoid them for my own well-being, partly because when people speak about hydrogen, so much of the focus is on the cost of the electrolyser, the efficiency of the electrolyser, what cost it needs to be for us to ship that hydrogen to the markets that might take it, like Japan. They are all important questions and ones that we should be asking. I think it's just that question that I want them to ask in the podcast is, will the water be available? What's the cost of that water? What's the opportunity cost of using that water in hydrogen? And is this the most valuable one? There's been a range of studies that have started to come around what it would mean in terms of the water's use in hydrogen in different forms. And certainly one study by Arup suggested that about a third of Victoria's water use, so about 150 gigalitres a year, would need to go into hydrogen if it's what was planned for in terms of making a full transition. The next one that I sometimes hear is about mine remediation. Again, you can imagine that that could be a really great use in terms of remediating mines and providing lakes. I think the only thing that I'd ask when people think about that is exactly the same questions that applies to all of the other uses of water. Is that the best use of water? Which type of water? Because it's really about finding a fit for purpose water that could be used, and what's the opportunity cost of doing that. There's also a lot of exciting technology and research. One of my colleagues, Li Gao, is here tonight. Leo, can you give a wave? So perfect. Who's been working on this area. And certainly one of the areas that we're most excited about that we're working on with RMIT and a number of the other water corporations is around pyrolysis technology to turn biosolids, which is dried sewage, into biochar. This technology is really key for us, partly about the costs of biosolids, which is predominantly water, but mostly around the fact that those biosolids contains PFAS. And as you would know, in terms of it being a forever chemical, and as we start to understand some of the implications of that forever chemical, the typical application of biosolids, which is predominantly to farmland and in agriculture, is no longer something that we are looking to do unless we can control that PFAS. So it's fantastic technology that has come from Victoria. A pilot plant has been done and it's taken out 99.99% of the PFAS in both the biosolids and in the gas. And we are now scaling up that to be its first production plant, and something that is closely watched around the world, because PFAS in biosolids is not only an issue that we face here, but is something that the US and Europe also face. There's a range of other exciting work that some of the other water corporations are doing as well. Yarra Valley Water has got a waste to energy plant that's located near one of its treatment plants. It takes in about 33,000 tonnes of commercial waste and uses the energy that's produced to run its treatment plant. And also some of the water businesses, in a desire to use some of the recycled water or treated sewerage water, have even started their own agribusiness businesses, so that that water doesn't end up back in our oceans but actually gets treated. So overall, before I finish, my key message that I wanted to leave with you and to invite questions on is just providing that context that the transition we're seeing in energy will shortly happen in water. If it doesn't shortly happen in water, then we are going to face a lot of maybe some of the negative consequences that we've seen in the energy transition, in terms of a community not understanding high costs because we haven't planned. And yet the good news is that if we start now, we've definitely got time. And I do ask, if you are ever thinking about water in one of your key processes, that you definitely think about the cost and other opportunity options that that water might have. Thank you.
We'll have the next presentation, and the guests can give their discussion. Okay, so now we welcome Professor Huanting Wang. So Huanting is an ARC Laureate Fellow and a Sir John Monash Distinguished Professor in the Department of Chemical and Biological Engineering at Monash University. And Huanting's research focuses on advanced membrane and nanomaterials for gas separation, water desalination and purification, chiral separation, ion transport and separation, fuel cells, and electrolysis. So Huanting published 460 journal papers and has patent transferred to the industry, commercialized by industry. And Huanting is fellow of FTSE, and also fellow of Royal Society of Chemistry and fellow of American Institute of Chemical Engineering. So today, Huanting is going to share with us smart materials and membranes for water desalination and resource recovery. Welcome.
Thank you for the introduction and hello everyone. So it's great to be here to talk about what I do. I guess today I'm going to focus on water related and the resource related. And my background is material science engineering, so I'm going to talk a lot about the materials. And all right. So the water purification and then the resource recovery from a chemical engineering perspective. So basically, it's water desalination purification, it's water solute separation, right? So how do we actually separate them? And then resource recovery, basically selective separation, right? So we want to get something out of the water, right? Not all of them, right? So that's a separation, recovery, sorry. And then how do we do that? So there's a different mechanism we can use to do that. Filtration, very simple one. So you got porous material, all small pores, and then just do the filtration, right? So, and anything larger than pores will be removed, right? So that's filtration. And also in the evaporation. So especially in the membrane area now, so people are doing a lot of work on the membrane distillation, right? So that's the water evaporates through the membranes and then condense, right? So we produce a pure water. And then also absorption process in the porous material. So material has a lot of small pores and then absorb, contaminates ions, and then we can actually recover that from water. So that's three different main mechanism we can do that. So let me just start with the membrane-based water desalination, and then lithium recovery. So Laura already mentioned the desalination. So I guess the membrane desalination, what we call reverse osmosis process, our process, right? So and then the seawater, was drawn into the desalination plant. And then we have a pre-treatment, right, to remove the suspended particle microorganism from water. And then the water is pumped into the membrane module that's called our module, right? So the membrane now is doing really well because the membrane can remove 99.8 or something, even higher percent of salt out of water. So the water, coming out of a membrane module actually very, very pure, right? High purity water. And that's not very good. So and then for making it drinkable, and then so we inject mineral back into the high purity water. So people talk about energy consumption of our process. It's all about, because in the process, very high pressure is required to push water through the membranes. So that's why the process consumes a lot of energy, electricity, right? And then theoretically, so we don't really need that much energy. So that's why the process need to be developed, improved, and the material also need to be improved. And so I just highlighted the one recent breakthrough in the publishing science, not my group, right? You see the author there, right? So people have been looking at different materials for the our process, right? So we all know, in the field, we all know that polyamide is a typical gold standard for the industry, right? But now the new type of material, polyester, actually been developed. So the only difference is, it's biochemistry, right? So just a different monomer, in the process, right? And then the material produced through that monomer actually works much better, in the than the polyamide. So polyamide has been there for like over half decades, half century, many years now. So I guess, in terms of performance, the three parameters very important: water flux, so how much water actually can flow through the membranes, and then also salt rejection, so how much salt is being rejected, and also another very important one is boron. Say polyamide is not very good at rejecting boron, right? And then now the new material actually can reject boron quite well, so that's good. And then also the chlorine resistance is very, very important for the membranes, right? Because in the process, very often chlorine is injected, and then to prevent biofouling of the membranes, right? And then the polyamide is not very stable in chlorine, so that's the problem, right? So and then make the process more complex, right? But now the new membrane actually can be very, very stable. You see the red one, it's the flux and the rejection, very, very stable, very, very stable, in chlorine. So that's a really exciting development, right? The paper just came out very recently, right? And then another new materials, it's a graphene, people talk about 2D material, two-dimensional material. So in the engineering science area, so people are looking at a lot of different new materials, right? So graphene is just like a atomic thin carbon layers, right? So itself, it doesn't permeate anything, it's non-porous, right? So, but I guess by processing graphene into the membranes, create a lot of small pores, right? And also the interlayers, layer by layers, and then the water can go through it, right? So that's what we got, one example. So we can make that into, the ceramic disc or ceramic tube, right? So that, because then we use a high temperature process, right? And then I just want to compare the graphene membranes, because there's all this, still in the lab, not being commercialized yet, right? So of course, we are doing a lot of work, other group also doing a lot of work, try to commercialize this kind of membranes, right? So I just put the comparison there. So graphene membrane compare with commercial PTFE membrane. So you can see that the flux is much higher. So that's for the membrane distillation process, especially important for the near zero liquid charge discharge, process, right? Because you can remove the water, 90% of the water and something like that, even higher, So very little wastewater is produced in the process, right? And then the material, so we're doing material, we like, we play with a lot of different materials. So previous case, that's just a graphene. And then also we look at other materials, Maxine, for example, that's a very common one. And then we combine them together. So you can see that we got a one layer graphene, one layer Maxine, and then one graphene and then Maxine, right? So the structure, what we call the pore structure is a heterogeneous heterostructure, right? So that's quite interesting because fundamentally you can see the TM. That's a real image, okay? So that's a high resolution TM. So you can see that the materials like one layer, this one layer up, right? So quite interesting, right? So then we found this kind of material actually has a very different properties. So then water go into the small pores, and then the density, viscosity all change, right? So that's why this kind of membrane actually has a potential to have a very high flux, right? Because of the water density of flux all change, right? And also the kind of membrane works very well for the organic solvent. So that's probably the next step, so organic solvent, not much research on that. So we have done better work with that. And so I'm going to skip on this. And then, so the next one is about the resource recovery. So I will just give a lithium extraction as an example. So a lot of now the lithium we use in the lithium battery, right? So that's extract from the spodumene rocks, right? So in Australia in particular, right? So and also half of them actually extract from brine, right? So mostly in South America, right? So the process to do this basically just a very traditional method, solar panel, right? So just solar evaporation. It takes like 6 months to 2 years to get enough concentration, and then you use a chemical like a sodium carbonate to precipitate lithium, right? So the process, you can see that it's very long, takes a very long time, and also it consumes lots of chemicals, and it produces lots of chemical waste, right? So that's why we've been looking at developing membranes. So we have Monash have a startup company called Electrolysis, and then they try to commercialize the membrane we develop in the lab. Not this material, but I just want to show you an example, right? So we basically look at the different porous materials, and then with the too much chemistry, I guess, and then with the small pores, the windows, and then the lithium actually can, or sodium, what we call monovalent ions can go through a lot faster than magnesium ions, because in the brine, so very often problem with the magnesium, because when you do the precipitation and then you precipitate lithium with magnesium, right? And then you get a mixture, right? So that's why we need a membrane to take magnesium out first before you do the precipitation. So that's what we're trying to do, right? And then you can see that the metal ions. So we tested different metal ions, so lithium, sodium, potassium, magnesium, and calcium. You can see that, and the membrane actually transport ions in one direction. You see the other direction, and there's no transport from the other direction. And then the magnesium ion is right. Is here. So it has a very low current. So that means the magnesium ion is blocked almost 100%, right? So that's really interesting material. And also, we look at other materials, so because of the lithium-ion batteries, so especially now the solid lithium-ion battery being developed, because it's safer, so we're just trying to use the solid electrolyte developed for lithium-ion battery to do the lithium separation, because those materials actually are really highly permeable to lithium ions, right? And then the question is, can we actually use it for separation? Because, lithium ion can go through really quickly, but we want to block others. Only lithium goes through it, right? So that's what we've been doing, right? So we develop the membranes, and then we only allow lithium to go through it, and then reject all others, right? So the company I just mentioned, Electrolux, actually is commercializing this material, and then hopefully, I don't know how long it will take, next few years, and then we can see something out. And then another thing I want to mention, is the ammonium recovery from wastewater, right? So actually, Lee is sitting there, and then he recently received a ARC industry fellowship through Monash University, and then actually I copied all these numbers from his proposal, right? So you can see that there's a lot of ammonium actually in wastewater, right? Swine wastewater, non-fuel addition, right? So if we recover all the ammonium from wastewater, actually that can meet 20%, almost 20% total amount of ammonium demand for the Australian agriculture industry, right? So that's quite significant. But the problem is, how do you actually recover, right? With a very low energy consumption, right? And then so that's what we're trying to do, So we're trying to develop ammonium selective membranes. So if you have questions, right? Okay, and then also, just aware of the time. Okay, doing quite well. Yeah. So I'll try to finish it within 5-10 minutes. Yeah. And then the small materials for desalination and the lithium recovery. And then so I mentioned that solar evaporation pump. So we see this being used for many years, right? And then so if you look at the solar pump, and then see the temperature gradient, right? So because of the solar just goes through the water and then to the bottom, right? And then you can see that to the bottom, the temperature is higher than the surface, right? But we all can, in chemical engineering, and then we know that it's not good because we want water from evaporate from the surface, right? Not from bottom, because bottom it doesn't matter how hot it is, water cannot evaporate, right? So that's why over 10 years, yeah, many years ago, my student joined me from Peking University, and then we came up with the ideas. So can we actually do something differently, right? So and then what we did is just develop the material, which can absorb sunlight very effectively and also float on surface, right? So that's quite interesting. If we can do that, and then we can actually improve the water evaporation rate. And then, so in the lab, very simple one. So we just use the carbon is very cheap, right? And then also we added the iron oxide. The reason for that, because iron oxide is magnetic, so we can actually recycle that using magnetic field, right? And then it's a very cheap material. And then why carbon can float on water? Because we make it porous, right? So it's highly porous material. And then the surface, you can see the contact angle over there. So it's hydrophobic. So that's why the carbon actually can float on the surface, right? And then and then we, of course, we see the very significant enhanced water evaporation. So we just use a very tiny amount of material. You can see the number over there, 115 grams per square meter, very small amount of material. And then we can actually enhance the evaporation rate by, 2.3, up to 0.3. So we didn't really control the experimental condition, just, we did in the lab. So that was quite interesting. I didn't realize that. And then after that, I stopped doing this. And now I found a lot of other people start doing that, right? And then, so that's why I often, attend the conference and I got a question from, I thought, why you stop doing that? Now so many people follow you, right? And then, so very recently, I saw the review articles published in Advanced Materials. So you can see the area now is growing very significant. Thousands of papers published after us, right? So that's good, so at least, people are doing that, right? Okay. So you can see a lot of applications. Okay, so using what people call an interfacial solar evaporation, because it's a very simple change, right? So basically just heating the bottom water, right? And now we just heating the surface water. That's all, right? That's what we do, right? And then couple more slides, and then we also develop the absorbent. So the material at the mouth, similar to the material I just showed you for the ion transport. So that's the metal organic coordination polymer, right? So it's crystalline materials, and then just like the crystals like this, right? And then so we function on that. We put a organic functional group into the pores, right? And then this particular molecules actually quite interesting, sensitive to light, right? So UV light and then the visible light, right? So when the material is exposed to the UV light or in dark, and then the material become ionized structure, right? And then that material become absorbent salt from water, right? And then this material can be recovered. The salt can be recovered, just expose the material to the sunlight. And then we can wash the salt out of the material very easily. So that's quite interesting. So we did this in the lab. We found we can actually remove water, remove salt from water quite effectively. And then also we can regenerate absorbent. So you can see that within few minutes, right? So we can actually wash the salt out of the material. So that's the very interesting concept. And also, and the question is, how do we actually do this on large scale? So basically, we can imagine, we have a lot of column, right? So we can column, and then water flows through, and then salt being taken out, right? And then until the saturation, and then we can stop that, and then we do that on another column, right? And then we can regenerate that column, right? So just use light, right? So we can do that, right? And then so that's quite interesting, right? So to actually remove salt from water and to produce pure water, right? All right, and so I think the one more slides, and also this material actually can be functionalized to absorb lithium in particular, because if we have a right structure, and then the material can be selective, right? So that's something we've been trying to do for a long time, and finally we got the material, because in the previous case, and then basically the material is not selective to different salt. So basically just take all the salt out, right? But now we want material to be selective, right? To recover lithium from water, right? All right, so I guess I hope probably it's not too boring. And then give you enough examples. So basically, today I just want to highlight some of the new development, emerging technology in the water related area, right? So membranes, absorbent, and we can use renewable energies, solar, to do a lot of separation. And thank you very much.
Thank you very much, Huanting. So now I'll probably invite both speakers now to the front, and then you can take a seat there.
Okay,
yeah.
all right.
Yeah, so well, water is so important in our life. This is really fascinating to know that not only for drinking, but also for almost like every sector, water is playing a very important role, in particular in the current situation where new technology is emerging and environmental conditions changing. And then water sector is actually facing the challenge, but also in the meantime, we also discover lots of opportunity, as just Lara mentioned. So I guess we need to be aware of this and then get prepared. So I think now we have about 20 minutes. I do have my question, but I think I will leave the opportunity to the audience to ask first, and then if there is any time left, I'll ask mine. So please go ahead.
Thank you. I have a question for Lara. Thank you for your presentation. It's about a scenario you put up which said that there was a significant amount of either recycled water or manufactured water, I think you call it, into the future. All of that manufactured water is going to be more expensive than what we're doing at the moment. I presume we're not going to build too many more dams, and I don't know that you have the ability to push costs of water up. So my question is really what levers do you have to encourage industry and others to use water more effectively, to recycle it, to do the kinds of things that you're suggesting?
Yeah, thanks, Jeff. And I have to say, I am one of the fortunate people to have gone through the University of Melbourne where Jeff was there. So I feel very privileged to be here and to receive a question from you because I asked you a lot of questions through my course. I think it is an interesting question. We did see bills rise by about $150 to $200 per household when we put the last desalination plant in. And we can see that we probably need to be a larger plant and we're going to need more of them. It's really clear. In terms of what we can do to help people, particularly industry, potentially use less water, I think one of those key mechanisms is actually price. So we have had flat water bills for the last 10 years, and that's been a great thing in many ways. But it also has probably meant that people haven't fully appreciated the true value of water. So I do think that will be one part of the important mechanism. And there's ways we can support people. Obviously, if people need water. So for those that can't afford it, there's different ways we can look to make sure that they get the water they need. I think the second thing that may or may not happen, but I think would definitely happen if we had another millennial drought, and we see it with customer focus groups, is that there'd be increased pressure on industries to talk about water. One of the things that we discuss is in 10 years' time, when we start to see the same type of carbon counting that for water, so that you know for your product how much water this, a particular cereal used, or how much water that almond used, or how much water this shirt used. Because in some ways our budget isn't really 155 litres per day. It's probably far more like 500, 600 when we think about all the different things that we consume during that time.
Thank you very much. We have a question here.
I think it follows on nicely from that. I'm from the agricultural science side. 39% of the water used in agriculture, and I suspect part of the other industrial use also includes a component for the food industry.
Yes.
So that's a lot of water, and there are technologies in agriculture to use less water. We know this.
Yeah.
They're developed, and there's a whole lot more that seem feasible. They rely on water price. Levers are one thing, as has been mentioned, about what the public will put up with. What can we put up with in a political sense?
Yeah.
Trying to trade off between the urban and rural divide, because we have a number of people disadvantaged in rural industries already. And that's the political issue that will govern this. Whereas the people who are using a lot of water and trading in water tend not to be the impoverished part.
I mean, I think it's fascinating when I think I fully appreciated where we were from a water situation and then looked effectively at that pie graph. It's partly that there are so many good uses of water that we'd want to support, and they are each probably going to grow, including agriculture. I think some of our options around that is using recycled water. Again, it depends on the class for agriculture. And we certainly have a large project that we have out near Pakenham, which for those people that would know it, has a lot of the asparagus that's grown across the nation and a range of other areas as well. And there we can treat the water through some of the mechanisms that my colleague mentioned to be either what we call class C, so okay for sort of agriculture, or take out some of the salt as well, using reverse osmosis, so that that water can be used for agriculture. I think we'll start to see more of that usage come. One of the issues with that sometimes is if you are not near a treatment plant, then the cost of building the infrastructure to get that recycled water to you can mean that the projects don't stack up. So as the price of water goes up, then more of those projects will stack up as well. I think it is really important to support agricultural users. And again, when we talk to customers, it's something they definitely want. So when we talk to our customers about do they want their prices to go up, once you explain what that would mean and what it would enable in terms of the environment, in terms of making sure that food can be grown, that there's jobs, that there's parks that are green in their area, most people are actually okay with it going up. I think it's about how we have a conversation that is a slower conversation to say, this is coming, we're going to need to get ready for this, how do we manage it? And that's what I feel like is one of the key lessons from the energy transition. If it happens and people don't feel part of it, then naturally, I think all of our natural reaction is like, no, why don't we just do this or this? Having that conversation we have seen with customers, when you explain it, they do understand.
Thanks, Lara.
Yeah, I've spent a fair bit of time in the last decade working in Southern Africa, and in particular looking at the demand on a whole range of things. But for example, water is often in very short supply.
Yeah.
You'll find that industrial operations, particularly mining, are often very short of water. The local communities are short of water, and often a mining process, for example, may have to decide whether or not it can go ahead based on the local demands for the community.
Yeah.
So what you see is a proliferation of desalination plants developing on the coast. So where does the responsibility lie when one makes a decision about this? Is it the decision made by the company in partnership with the government or the local community? How do you see those three things interplaying?
Yeah. I wish I had the right answer for that, but I do know the scenario that you just painted when I was living and working in the United States before this part of my career. And I know in Arizona there, the water board used to come when they were having discussions about investment into the state. And there was certainly one large data center that didn't get up because they just didn't have the water available for what that data center wanted. So I think if we don't get this right, then we definitely see constraint playing out. I think this is part of that conversation with the community around if we do want to have water for all these uses, it's not falling from the sky anymore like it used to. And to your point, Jeff, we can't actually build more dams because that goes against some of what we just spoke about in terms of that environmental water and the need to have that flow going through. And so we are going to have to talk about as a community what we want, who pays and how we share that because there's no other way. And hopefully there's some great technologies that come through that mean that we can use less water in different processes so that we can use the water for some of those other needs up there.
Just following up from your nice segue into technology. Have we got the settings right to translate all the great research that's coming out on membrane and separations and that? And what's the role of water authorities in actually, because that's going to be the end user and probably the regulator of if this is going to create water that can be used. So what's our system like that's going to help get these great innovations across into commercial reality? And what could we do better?
I think in this case,
Yeah, I think I might have a biased view about how we are as customers.
Okay, all right. So I guess in my own experience, right? So we've been working with the industry very closely, and then trying to develop some of the new material membranes and technology, and then commercialize the question whether we have a right structure. I guess that's a big question, right? So I guess just like any other technology develop in the lab and then to the market, right? I guess we now see more support, right, from the government and then from the industry. It's in particular, we're very happy to see actually we can have a support and an investment in Australia. So in Monash, we already established to start a company. So to commercialize the membrane technology developed in my lab.
Thank you. I think maybe Lara, you want to?
I think the exciting part about it is having gone to water conferences globally is the focus that is on the Australian water corporations because of some of the innovation that's been done. So, and also that our system is quite similar to those of a lot of other countries. And so if it can work here, there is that sense that it can work in other areas. Certainly compared to some of the other sectors I have been in, we are sometimes slower to take up technology, but I think that's partly the public health overlay that I haven't necessarily had in some of my other sectors. And so particularly anything that goes to drinking water or water that then could end up obviously in the ocean and around what that might do for marine environment, I think it does create somewhat an overlay. Certainly in our organisation and other water corporations, we know that it's the future. There's no way I can solve that pie graph, and partly what's been raised because the community just couldn't take it if we just put in more desal plants and pay for that energy and cost. And so some of the work we do invest a lot in research and development. I think it's one of the reasons that people come to our corporation, not necessarily because they're working in that team, but because they can see it's an organisation that invests in that. And there's a lot of excitement around that. That said, I think we probably could be faster in terms of how we pull it through.
Yeah, Southeast Water has really played a very important role in supporting the local and also national, international this kind of technology innovation. So I guess if we have more like industry supporting, so that's also very critical for technology translation. Please go ahead.
Yeah, just a question about recycled water going into agriculture and microplastics.
Yep.
What's being done about that? Is that an issue, and what's available to mitigate?
Yeah, so I think that's a key part for also our water just going into the ocean as well. So one of the key areas I mentioned was sort of around PFAS, which is true of sort of solids and water treatment. And I do have to say that Lee, who is here, I'm going to quote him, but he's definitely the person you want to speak to at dinner in terms of that, because he and some others did work around looking at microplastics. And I know in speaking to him, the different types and what causes it and the different nature of the fibres, and the majority is, or the large part is caused from our washing machines and what it takes through. That although a lot of our treatment plants are old, we've got 4 that are getting upgraded this year, that our treatment process, although it wasn't designed, do remove quite a proportion of them. And then it's looking at the different technologies, both biological, chemical, and also physical, that can then take them out to different levels. So it's something that we measure. I think it's also something that increasingly, rightfully, consumers are asking about and wanting to understand. I think it is really important, if I take PFAS as the example, that we remove it, obviously, from water and also solids. But it's also the wrong end of the process to be focusing on. Like, we should remove it, but till we get rid of it from a source perspective, we're just going to be removing more and more of it. So we should absolutely do our part, and it's important, but I feel like the energy should be up here as well to say, how do we take it out?
Do you have time for a couple more questions? This one first, and
I
then
wanted to follow up with PFAS
yeah.
And the biochar.
Yeah.
You talked about removing it. Is the PFAS actually destroyed? Or
Destroyed.
It is. So you
Yes.
can't just remove it somewhere.
No, and actually we did the first trial and we could see that it was destroyed from the solids. And I think we're quite excited, and then really thought, actually, are we definitely sure it's destroyed from the gas? Like, have we just created a different problem here? And I think that's why we are now investing in a production plant from it, because it does. And so, yeah, it was really exciting to get that.
There is a commercial process for destroying it in soil by baking it in what looks like a cement kiln.
Yeah.
So it looks like heating in the presence of the organic stuff.
There's quite a few different processes around, and I think it's an exciting space in terms of there are competing technologies now getting really to that stage. It's then really around how efficient it is from an energy perspective and emissions perspective, and also can you keep the process going? Some of the other processes have issues with needing to shut down for cleaning in other areas. So it is a space, again, which I think is exciting, that Australia and Victoria in this case is really leading it and pushing. And maybe that's the other thing. I think the nice thing coming from energy is that water professionals are very humble, which is wonderful, but you really have to extract out like the great work that they're doing. I'm used to a lot more sectors where they are front and forward in saying it. So yeah, I think that will be an issue that clearly needs to get solved, and there's some great work.
Thank you.
My question is directed towards the somewhat lonely second speaker. Also a technical one. I was quite fascinated by your comments on light sensitive membranes.
Yeah.
And particularly using the spiropyranes.
Yeah.
Water treatment often has to be carried out at 50 degrees Celsius.
Yeah.
And sometimes as low as, if you're in poor old cold Tasmania, down around 3 or 4 degrees. And spiropyranes are not particularly temperature sensitive. They are temperature sensitive and they tend to back react.
Yeah.
I wonder if you thought of using derivatized thymines.
Yeah. That's a really great idea. Actually, we also look at different mechanisms to the temperature responsive material as you mentioned, right? So actually we've done some work on that. Yeah. Thank you. Yeah, we can discuss more.
Thank you.
Yeah.
One last question.
Actually, I've got one for each panelist.
Please go ahead. Please do have
Quickly, I was intrigued by your conversation about the spheres that some of the technology is surrounded on, and whether there is any opportunity for synergy between your technologies and what I've been reading about in the United States with the 96 million black holes that are deployed over reservoirs to stop the formation of bromine. So can we combine technologies for multiple applications?
Yeah, I think there's opportunity. Yeah, there's opportunity for further development of materials and to combine. Yes. Yeah.
And we've got collaborations,
yes,
connections, and networking globally to
yes.
have those conversations.
Yeah. Thank you.
And my last quick question, the jurisdictions in Australia for of interest around water, state and federal, depending on your answer, do you see a role for ATSI in getting that slow, long conversation going?
Absolutely. I think the other part is there's, different water availability and costs all across Australia, and actually, I just joined ATSI last year, and there's already a working group in water looking at an explainer around sort of fit for purpose water and the right type of water for the right uses, and the importance of water security and resilience. Partly what I sort of didn't explain as one of the other factors is, yes, we have those reservoirs, and all of those equations are not sort of necessarily based on the fact that if we had a bushfire and it took out one of those reservoirs, that would quickly drop. So I think that work is started off in terms of how do we explain what's changing and why we can't build more dams and the different types of water that we might need to think about. So yeah, that work is underway.
Now, are our jurisdictions united? Yeah.
Yeah, interesting question. There's actually different approaches in different states on that. Yeah, some of it's good in terms of learning what others have done. So in Western Australia, for instance, they take recycled water and put it back into the water treatment system and sort of shandy it, if you like, with I think that's not the official word, but shandy it with the water system coming through, and people are accepting of that in terms of drinking it. In other jurisdictions, we've seen political campaigns lost because people didn't want to drink poo water. And so sometimes that is quite helpful to have a leading state so that we can look and point to that and see that the community has accepted it and what communication messages has worked. I think one thing we haven't had is a national water agreement for quite a long time. And as you probably know, that is being re-looked at from a federal perspective. And I think that's a really good thing.
Thank you so much. Thank you for the questions, and thank you so much, Lara and Huanting, for the very, very interesting answers, and also to have this fascinating science and also the frontier of industry to present to us. So to show our appreciation, we do have some small gifts for
Okay.
So these are the 3D printed vase. So yeah, so you can see it's really, really nice. So you guys can probably
choose.
I usually
Oh no, you to go this one.
All right.
Thank you.
It's very light. It's 3D printed, fully recyclable.
Okay, all right. Okay.
So
Thank you.
it's really great to have this hot discussion in this cold weather. So I hope that we could continue this discussion and find more opportunity than challenges for water sector, and also for make use of the resources, and then to make good for benefit of our life. So thank you so much again for your time and commitment, and thank you so much for making this event tonight. Thank you.